Hello, my name is Daniel Townley, and I'm here to present Composable Cachelets, a new cache partitioning architecture for protecting enclaves from cache side channel attacks. I worked on this paper as a PhD candidate at Binghamton University with collaborators at Binghamton University and TOBB University of Economics and Technology. Trusted execution environments, or TEEs, such as Intel SGX, have received increasing attention from both the research community and industry. Unlike classical security solutions that relied on operating systems to enforce isolation between processes, TEEs use specialized hardware to enforce enclaves in which sensitive code can run without interference either from other user processes or from the operating system itself. As a result, TEEs can run sensitive software even when the operating system is untrusted. Despite these benefits, TEEs have proven vulnerable to cache side channel attacks. One example, a classic example, is a prime and probe attack, where an attacker populates a cache with its own data, allows the victim to write to the cache, and then measures the timing differences in data retained in the cache and data evicted by the victim to reconstruct sensitive computations. Current TEE solutions do not account for these micro-architectural side effects and can be bypassed using these attacks. A logical solution to these attacks would be to extend TEE partitioning to caches. Unfortunately, past proposals for cache partitioning are not compatible with TEE's computation models. Some partition strategies are enforced by the operating system, and because they trust the operating system, are not compatible with TEE security models. Other strategies are implemented purely in hardware and so overcome this problem. These strategies, though, typically modify the cache replacement logic to enforce partitioning at the granularity of cache ways. In many TEEs, however, enclaves can be relatively small and have a small memory numerous, and thus these relatively coarse granularity partitioning can both be underutilized by enclaves and have a disproportionate impact on non-enclave processes sharing the processor. These challenges demonstrate the need for TEE-friendly partitioning strategies, which are both hardware-enforced and fine-grained enough to accommodate enclaves of various sizes. Our solution, Composable Cachelets, or CC, is an effort in this direction, focusing on large L3 caches where fine-grained partitioning is especially important. CC partitions the cache into two-dimensional regions called cachelets. The cachelet consists of, can span multiple ways, taking advantage of associativity, but only occupies a number of sets within the way. To accommodate enclaves of various sizes, CC can chain together multiple cachelets into a larger structure that we call a virtual partition. Importantly, the cachelets composing this partition do not have to be contiguous, making it simplifying the process of allocating partitions as enclaves enter and leave the system. Additionally, CC allows non-enclave processes to make use of any portion of the cache which is not allocated to active cachelets. To achieve compatibility with TEE security requirements, CC uses lightweight hardware to enforce cachelet boundaries. The first component of CC is the address remapping logic, and this is responsible for ensuring that cache accesses from an enclave are directed to enclaves assigned to or rather cachelets assigned to the enclave. To implement this remapping, each core is extended with a virtual partition table, or VPT, which holds cachelet mappings for the enclave. Each VPT entry contains a set offset bits and way offset bits indicating the location of each cachelet assigned to the enclave. When an enclave accesses memory, the high-order set index bits are used as an index into the VPT, and the set offset bits are used to replace the high-order bits of the address. This forces the address to be mapped to one of the sets, which is occupied by the corresponding cachelet. Additionally, the way offset bit from the entry is used to generate a mask, which is then used by the modified replacement logic of CC to force the address to select a way or to select a way which is assigned to the cachelet. And these two mechanisms ensure that the address is mapped to the assigned cachelet. To enforce partitioning between enclaves, CC also must ensure that the enclave each enclave is assigned unique non-overlapping set of cachelets. To enforce this, CC allocates cachelets from a common or a shared cachelet free list, or CFL, which is a hardware structure similar to a register free list. The TEE logic is augmented to pop entries from the CFL when a cachelet or an enclave is created and return them when the enclave is destroyed. This ensures that no two enclaves will receive overlapping cachelet allocations. Additionally, when a enclave yields the core due to a context switch, the VPT contents are stored in the enclave metadata provided by the TEE. This exploits an existing mechanism provided by TEE, which is used to store hardware states such as register and flags, and this mechanism is simply extended to include the VPT. In addition to protecting enclave data within cachelets, CC must also maximize the availability of the cache to non-enclave programs. To track which sections of the cache can be safely accessed by non-enclave programs, CC maintains a set of bit arrays that correspond to the layout of cachelets in the cache. When a non-enclave process accesses memory, the high-order set index bits are used to access a row from this structure, and this will then be row will then be used as a mask also by the replacement logic to prevent the address or the access from replacing a cache line which is owned by a cachelet. To evaluate the performance of CC, we modified the Gem5 architecture simulator to implement our addressing scheme and evaluated the performance impact of running a variety of benchmarks. All of our simulations were performed on a 16-way 8 megabyte L3 cache. To evaluate CC's impact on programs running inside of enclaves, we ran a collection of cryptography benchmarks representing typical enclave workloads. And evaluated the impact in terms of instructions per cycle. In our most conservative configuration, we used a 256 kilobyte partition and a single way of associativity, and found that although the maximum degradation was 8.4% for BigQuake, most applications experienced a minimal slowdown, which was in fact negligible in some cases. To evaluate the impact on larger enclaves, we also ran a number of tests with Spec 2017 benchmarks, and found that even for our smallest allocation of 512 kilobytes, we saw modest average performance loss of 6%, which dropped substantially as we scaled the partition. A few programs, like MCF, proved to be more sensitive, but the performance of these programs improved as we scaled up the partition allocation. Finally, we ran some additional experiments to evaluate the effect of cachelets on non-enclave processes. For this experiment, we focused on the spec benchmarks that suffered the most when forced to run with a reduced cache footprint. We saw that even when cachelets occupied half the cache, the average IPC for these non-enclave programs declined by just 2.7% in the most extreme case, and even the minimum was 7.1%. In addition to our performance results, we also estimated the impact of CC on processor area and power. For this, we used the McPat architecture simulator to derive our results. We observed that both the CFL and VPT structures closely resemble existing cache structures, and so our estimates for these components were based on McPatt's simulation for the similar conventional cache components. We also modified McPatt to model some additional tag bits, which are required by our enclave addressing scheme, or cachelet addressing scheme. Overall, the changes were less than 1% in all of these categories, and with the largest overhead imposed by the additional tag bits. This concludes our presentation of composable cachelets. Before closing, I just want to go over briefly some other areas that we address in our paper, particularly more additional discussion of our hardware implementation, including more detailed descriptions of the mechanisms described, as well as performance results for additional benchmarks. Most significantly, our paper also includes a detailed formal evaluation of our system's security, which is based on the operational semantic model, the operational semantics models of the cache. This model can also be extended to evaluate other partitioning schemes in addition to composable cachelets. And that concludes my presentation, and I'd be glad to answer any of your questions.